mass on hemisphere.
Hello. Last time we derived the Newton's second law in polar coordinates, and today we'll see some application of it. So we have a problem called particle sliding on hemisphere. So we have a particle of mass m initially at rest on top of a smooth hemisphere of radius r. At time equals to 0, phi equals to 0, phi dot equals to 0. And the particle starts to slide down the surface of the hemisphere, and what we want to know is we want to find the angle at which the particle leaves the surface of the hemisphere. Okay, so first of all, we'll start by drawing a free body diagram of the particle at this position. So at this position, we know that since it's in contact with the hemisphere, there will be a normal force perpendicular to the surface of contact. So say that's the surface, this is my normal force. And we know that there is gravity, mg. And we define this to be my r hat, and this to be my phi hat. Okay, so now we can write down my Newton's second law in r. We have m r double dot minus r phi dot squared r hat. We can get rid of the r hat because we indicated here is r. And just based on this free body diagram, we know that we have a n and we have a mg towards the negative direction. So we would have normal force minus, so here is my angle, here's my angle phi, so we would have cos of phi mg. Okay, so that's in r, and in phi, what we will have is m times r phi double dot plus 2r dot phi dot. Okay, and in phi we only have this component due to gravity, which is mg cos of phi. Now we have two equations, and we have a lot of unknowns. So we know that one of the restrictions that we have in this system is that the r is not changing. So my r double dot would be 0, and my r dot would also be 0. Okay, so that makes the problem much easier. So let's just write it out. I would have in r, I would have minus r phi dot squared equals to m minus cos phi times mg. And in my phi, I would have mr phi double dot equals to mg cos phi. Okay. Now I'll introduce a trick that's used a lot of time in physics. Basically, it's called the v dv dx rule. Okay, this thing basically says that acceleration equals to v dv dx. How do we see this? So acceleration equals to dv dt, and if we multiply top and bottom by dx, and we would get dv dx and dx dt, where this is just my velocity. So acceleration equals to velocity times dv dx. So what we can do here is that we can multiply everything by phi dot, which equals to mg cos phi dot. So what you actually need is not the v dv dx, but v dv dt equals to 1/2 dv squared dt. So that's what I actually used. So how to get from this to that? Okay, so what we can do first is multiply top and bottom by 2. So we will get we'll get this, and this is the same as 1 over 2 times v dv dt plus v dv dt. This is similar as using a product rule. So say I have d dt of v times v squared, so it's d dt of v times v. What I will get is dv dt times v plus v dv dt, and you can interchange this. So what you get is 1/2 dv squared dt. We can say that this term is equal to 1/2 mr phi dot squared d dt. When you take the derivative of this term, the two will go into the front. You have mr phi dot, and then you have to apply the chain rule, so you get a phi double dot. Similar to this case, you'd get d dt of minus mg sine of phi. Okay, yeah, I made a mistake here. Yeah, this is cos, this is sine. This is sine of phi, this is sine of phi, and so this is sine of phi. So this is cos of phi. Yes, okay, so let's rewrite it. I would have 1/2 mr phi dot squared equals to minus mg cos of phi d dt. Apologize for that. Now since so now we can move the right hand side to the left hand side, and and this would equal to 0, so we know that this term equals to some constant, because where the derivative of this term equals to 0, so this term must be a constant for it to be a 0. Now we have to use our initial conditions here to determine the value of c. So we know that phi dot equals to 0 at t equals to 0, phi equals to 0 at t equals to 0. So this term would just be 0, and this would be cos of 0 is 1, so c equals to mg. So we have phi dot square plus mg cos phi equals to mg. Okay, that's great. Now, yes, I also missed a m here. Oh, I'm so sorry for that. Now, what we can do is we can isolate this mr phi dot squared, because we know we have a mr phi dot squared here. So we will get mg minus mg cos phi, moving this term to there, multiplied by 2 equals to my mr phi dot squared. And okay, so we would have, and now we'll put this into this equation here. My n would be cos phi mg minus this term, so have mg cos phi minus this term, which is 2mg, and then minus plus 2mg cos of phi. So we will get 3 cos of phi minus 2, all multiplied by mg, which equals to n. So we know that m is non-zero and it's positive, g is non-zero and is positive. So the only way for n, our normal force to be 0 is when cos of phi equals to 2 over 3. If normal force equals to 0, that means the particle is not touching anything, and that's what we want to find, the angle at which the particle leaves the hemisphere. So here is our solution.